Last two sections we're going to look at are 5.4 and 5.5. Okay, we've already done the beginning of 5.4, which is kind of the basics with logs. And just to kind of review a little bit, I want to rewrite this expression, okay, in terms of a to the x, a to the y, and a to the z. I don't want to have a complicated exponent like that. So if we look at our exponents, there's different operations happening. There's addition in the exponents, there's multiplication, and there's subtraction. There's a rule for each one of those. Like when you would multiply exponents, when you would add exponents, when you would subtract exponents. So let's start with this a to the 2x. That's multiplication. When would you multiply two numbers together to get an exponent if you had a y? So what's the rule for when you're supposed to multiply exponents together? If you have, yeah?
1 to power to a power.
A power to a power. So one way you could have gotten a to the 2x is a to the x squared. So now we've rewritten the first term just in terms of a to the x. Right? It's a to the x to the second power. Any question on that? Now, the next thing is you're going to add. When do you add exponents? If you what? Multiply exponents with same base. So we're going to write another base of a. We're going to make it multiplication. And what do you think this one would be?
To the y.
Yep.
To the 3.
Yeah. So now you've got a to the x, which is really a to the x squared, which is a to the 2x. So this, if you did it off to the side, would be like that, times a to the y times 3. And whenever you have bases that are the same, add the exponents. So that's a to the 2x plus 3y. So we've got up to here now. Now, what's the rule for when you subtract an exponent? Divide with the same base. Okay. So all we did there was rewrite an expression that had a complicated exponent as a to the x, a to the y, and a to the z. So just rewriting. Any questions on that? Okay, so let's take a look at, I think we've done this problem before, this exact problem in the notes. But when we solved it, we did it graphically. Right? We talked about it when we did exponential growth. Okay, I think on Tuesday. And I think the answer was like 28, if I just remember from the notes, it was like 28.07 years. I think it was something like that if you look back. But it's a town that has 50,000 people. It's going up at 2.5%. How long does it take the population to double? Okay. So I want to set this equation up, but this time I want to solve it with algebra. I'm not going to do like graph in y1, graph in y2 and see where they cross. Okay, we're not going to do it that way. So this is exponential growth. Does anybody remember what the formula starts out for exponential growth? We'll do population as a function of time.
You start with the population.
Start with the population. Yep.
And then you do the population times the growth.
What goes in the parentheses?
It's like p times 0.025, right?
1 plus 0.0.
1 plus 0.025.
Okay.
Yep, 1 plus r. So I'm going to do that all in one step. And the exponent, t. Okay. So there's our formula. And we want to know when the population reaches how much? 100,000. So you're going to plug in 100,000 right there. Now, we didn't solve this with algebra on Tuesday because we didn't know how to get rid of a variable in the exponent. Right? You can't do arithmetic to get rid of a variable in the exponent. It might be a little arithmetic we can do here at first, but eventually, the only way to get rid of a variable exponent is with a logarithm. But before I do the log, does anybody see something I could do first here? On both sides? We can divide each side by 50,000. As far as arithmetic, that's all you can do to get t by itself. So 2 equals 1.025 to the t. Now, how can we rewrite this?
Log of 1.025.
Log, what's,
1.02, the base, which is 1.025.
yep,
And that is 2 equals t.
and t, like that?
No, 2 equals t.
Oh, 2, okay, equals t. Right. So that is our answer. Now, I just have to show you how to type that in. Okay, so there's our answer. The only thing we have to figure out is how to type this in. Now, why can't I just type it in? I have a button that says log.
Because that's the log base of 10.
Yeah, I have a button that's log base of 10, and I have another button that's log base what? E. That base is not a 10 and it's not an E. So, I'm going to show you guys how to type that in. And the way we type that in is to use what's called the change of base formula. So we're going to put this in, we'll put it in with 5.4. It all kind of goes together. So change of base formula basically says if you want to take the log with a certain base and a certain argument, there's actually two ways to do it. They come out exactly the same. You can do it with common log, or you can do it with natural log. Okay? You can do it either way. The way to do it with common log is you take the log of the argument and divide by the log of the base. And that's it. So take the log base 10 of the argument and divide by log base 10 of the base. So the only way to type something in with a different base is as a division problem. Or you can do it exactly the same with ln's. It doesn't matter which one you use, you will get the same answer. You can take the natural log of the argument and divide by the natural log of the base. What you have to remember though is the ln of the base or the log of the base goes in the bottom. The log of the argument goes in the top. Okay, so let's try that on our problem. And, let's see what we get. Now, let's do this out. So we get, and I remember, I think the answer in the notes was like 28.07 or 08, something like that, because I just looked back at it before class. So take the log of the argument and divide by the log of the base, 1.025. And yes, that is what you're supposed to get. Now, let's say you did it with the ln. You say, you know what, I'm going to do ln. ln of the argument divided by ln of the base. It's the same thing. Right? So I just pick one of the two ways and remember to do it that way. So it's 28.07 years. And that's what we just used was called the change of base formula. Okay. Now, any question on that? Now, as I was going through it, I said to myself, why would the change of base formula be later in the notes than when I need it? Shouldn't I have the change of base formula right where I'm going to use it? And that's because I just remembered there is another way to solve this problem without the change of base formula. Okay. What makes this problem a little hard like something, because you wouldn't see this in Algebra 1. Why not? Yeah.
The exponent's a variable.
The exponent is a variable. We don't like to have exponents as variables. So there's a rule that allows us to move exponents in front, but you can only do that if you have a what?
Log.
And if it's a log. So what you can do, right? Like if you had x squared equals 9, you are allowed to take the square root function of both sides, as long as you do it on both. You can do the same thing with log. You are allowed to take the log function of both sides. And watch what happens if you do this. It's going to lead us to the exact same thing. All I did was take the log of both sides. Now, what am I allowed to do with that t? I can move it in front. Now watch what happens. T log, it's t times the log of 1.025. Now, that's multiplication. How would you move the log to the other side? You would divide by it. Log 1.025, that's gone. Divide by log 1.025. How does that compare to what we just typed in on the calculator? It's exactly the same thing. So what we just did there was kind of a way to get around using change of base formula. If you didn't know it, you could take the log of each side. But if you know the change of base formula, it's faster. Okay? So this we got from change of base formula. That's the way I would prefer to do it. If you don't know that, you can still do it by taking the log of both sides, move the t in front, and then divide, and it ends up exactly the same. Any questions on that? Okay. So, in Algebra 1, sometimes you've got data like that, and you try to find what's called a line of best fit. Right? So you basically find the best slope and the best y-intercept you can that goes through your points. Now, if you had something like that, would a line be a good fit? No. Okay. This would be better suited to a curve. Okay. And with the graphing calculator, we can find a curve that fits that data. It's not perfect because the points aren't perfect. The points aren't exactly a curve, but they're close. So, these points can be modeled by what is called a power function. The only thing you have to do is solve for a and m. You have to figure out what those are. Now, we're not going to calculate a power function by hand. Okay? I'm going to show you how to do this on the calculator. Can you do it by hand? Yeah, absolutely. But we're not going to. Hold on one second. I'm going to skip over that. So, first thing we have to do is figure out, is a power function the right tool to use? Right? Power functions aren't perfect for everything. They're good for some things. If your data looks like it goes like this. If your data follows a pattern that's a curve like that, yeah, power model will be a good fit. So, the way we're going to tell if a power model is a good fit. First thing, this is what a question will look like. Okay, we're not going to do it yet because I got to still explain how to do it. But you're going to get a table of data. Okay? You've got to do something to this table. The first thing you want to do is take your table and take the ln of every number in the table. Right? So we had 8 numbers, I think, in that table. So we're going to type in all 8 numbers and take the ln. And then what I'm going to do is I'm going to look at those points that I just created, and I'm going to see if they look like they're in a straight line. So I'm going to take the ln of every number in the table. I'm going to graph those numbers and see if they're in a straight line. If they are, then that means we want to use a power model for our equation. Right? Just because something curves doesn't necessarily mean it's a power model. I mean, maybe this is like part of a sine wave. That's totally different. So not everything that curves is power model. But the way you can tell if it is to do this. Take your data and take the natural log of every point. We'll go through and do it. And then we want to find two things. I called this A. I think the calculator calls it something different. The calculator might use B. Let me check. Calc, power regression. You know, it's not going to tell me till I actually type in a whole set of data and do this out. So we'll see what letter the calculator uses, but it's not really important. Okay, but you have to find A and then find M. Right, and then we write our final answer. So your final answer is going to look like y equals ax to the m. And the calculator will tell you those two numbers, as long as you type everything in right. All right, so let's take a look at the data in example 7. First, determine if a power model is something we should use. And then from there, we'll use the calculator to find it. Okay, so this is really like a calculator skill. Right? And I think this is the last thing in section 5.4. Yeah. And we already did some of 5.5 kind of, so we're good. Let's go like this. Okay, so there's my data. What's the first thing I said to do to every number in that table?
Natural.
Yeah, we're going to make a new table of all these points where every one of them is the natural log. Now, technically, another way to do this, if you didn't want to make the ln table, is to use log paper. Right? I don't have any, but I can show you what it looks like. It's a little different. Definitely not something you're used to. But that's logarithmic graph paper. And the way it works is if you graph a log function on this paper, log functions are supposed to curve. Okay, remember from yesterday, they're supposed to look like this. They get very flat. Well, if you graph that on this kind of paper, like the kind of paper you're used to, that's what it would look like. But if you graph that on this kind of paper, it would take that and make it straight. That's the way this paper works. It takes things that normally looked curved and makes them look straight because the spacing isn't the same. Right? I'm not really going to get into how to use it, but I mean, kind of quickly, the way it's scaled, it's like, let's say this is where you start. You start at 1. This is 2, 3, 4, 5, 6, 7, 8, 9. That's 10. Now the next one is 20, 30, 40, 50, 60, 70, 80, 90, 100. And then 2, 3, 4, 500, 600, 700, 800, 900, 1,000. So it starts out going by ones, and then you go by tens, and then hundreds. And because of that scaling, that's what makes that's how log paper works. But we don't use it.
Imagine being like
So
known for that.
instead of using that paper,
That was messed up.
we're going to actually just do it out by hand and take the log of everything in this table, put it on regular paper, and see if it looks straight. So let's just go through and do ln of 1. That's 0. Okay, ln of 3. If anyone has the bottom ones, that would be helpful. 1 point. Remember, we're going to graph this, so a decimal's fine. 1.1. Just round it like that. ln of 5 is about 1.6. ln of 8 is 2.1. ln of 5, I already have that one. 1.6. Does anyone have 31.2?
That will be 3.44.
3.4. And the next one?
4.29.
4.3. And the last one?
5.07.
Normally I like a little more accuracy than just the tenth, but I'm graphing, so I can't graph much better than to the tenth anyway. So let's look at those points on regular graph paper and see if they look straight. So this is something you really just do by hand real quick. So 0, 1.6. Maybe about right there. 1.1, 3.4. 1, 2, 3, and right there. 1.6, 4.3. 1.6, 1, 2, 3, 4.3, maybe. And 2.1, 5.1. 1, 2, 3, 4, 5, maybe about right there. Do those look like they're in a straight line?
Yeah.
Yep. The straighter of a line they're in, the better power model is going to work. Right? So these are almost, I think, exactly in a straight line. So I would say a power model is the right way to solve this problem. So, any questions on how we just figured out that a power model is the way to go?
Or
I have to just do the ln.
Yep.
And plot it.
And plot it. Now, I want you to, now we've determined that it's appropriate. So yes, it is. If it was, now find it. Okay. So now we need to type these original points into the calculator. Right? This ln table is done. We don't ever need it again. That table was purely just to see if a power model was the right tool. Yes? No. Okay, so you can get rid of the ln table. Go back to the original. Okay, the way we type the points in is we go stat, edit. In L1, put all your x's. 1, 3, 5, 8. Hit the right arrow, and it'll bring you over to L2. I think that's 5. 5, 31.2, 73.1, 160. Now, if you already had stuff in there that you didn't want, you can just highlight the number that's there, and you can just type a different number right over it. Or, if you want to just delete things, you can press delete. What you don't want to do is go up to L2 and press delete. If you do that, it's going to delete the whole L2 column. It's going to be gone off the screen. And the only way I know to get it back is just reset the whole calculator. So, I mean, I don't care if we have to reset one of my calculators, but if you had stuff on your calculator you didn't want to lose, maybe you'd have to look up how to fix that without resetting everything. Okay, so don't delete L2. Right? That'll mess it up. Now, another thing is you don't have to use L1 and L2. The reason I do it that way is because the default, the automatic for the calculator is to assume x's are in L1 and y's are in L2. If you do it that way, it's less work. If you don't do it that way, then you have to tell your calculator where you put your x's. Oh, I put my x's in L6, and I put my y's in L4 or something. Right? But if you put them in L1 and L2, that's what the calculator normally goes with. Okay. So any question on that part? Right? So we did stat, edit, you type everything in, it's saved as you go. You don't have to save it, it just automatically saves it. All right. So now, let me go back here. All right, so we got our data. Now you want to press stat again. This time we're not going to go to edit, we're going to calculate. What do we want to calculate? This is called a power function. Okay? That's what we want to calculate. Some calculators call it a power model, power regression, power function. It's all the same. So, under calculate, if you scroll down, or actually scrolling up might be faster. I don't know. So we've got linear regressions, quadratics, cubics, quartics, On my calculator, option A is a power regression, okay, or power model. We're going to hit enter on option A. Now, my calculator automatically assumes I put the x's in L1 and the y's in L2. That's why I did it that way. If you didn't, you could change that. If you look at all the blue numbers above 1, 2, 3, 4, 5, 6, you have 6 lists. So let's say you put your x's in L5. You could press second 5, and now you just said it's in L5. Okay. But I always put them in L1 and L2. So second 1. Okay, I don't have to adjust anything. Just go down and calculate. Hit enter. And it's giving me my power model. Okay, let's look at the letters that it uses. It uses A for the number in front of x, and it uses B for the exponent. What did I use? So I used A for the number in front of x, and I used M for the exponent. Just the calculator uses B, our textbook uses M. Just the way it is. So, we want to round this appropriately. You really don't want to write 4.999993839. What do you think A really is? It's 5, right? If there's 4 9s there, it's 5. Okay, we'll just go with 5. 5x to the. Now, what do you think B is?
1 2/3.
It is 1 2/3. If you have the same decimal repeating 4 or more times, 5 times, we can assume that that decimal would just keep repeating. Why doesn't it keep repeating? Because the data that I gave you was only accurate to 1 decimal place. Maybe if I had given you like 3.42 and 4.35 or whatever, your data would be a little bit more accurate. I mean, that's still pretty good. I mean, for only having tenths in the coordinate, that's a pretty good value for B. So 1 2/3 is what, 5/3? Okay, so there's your answer. So what I want to do now is I want to see how good that answer is. So we've got our points. What I want to do now on the calculator is go to y equals. I want to go up to plot 1, and I'm going to turn it on. So what I'm doing is I'm turning on one of the scatter plots. I'm going to check and make sure that the scatter plot is set up the way I want. Second, stat plot. I'm looking at plot 1. It's going to use L1 and L2. Is that where I put my numbers? Yes, it is. If it wasn't, I could hit enter and I could change it. I could say, no, my x's are in L3. But no, my x's are in L1, my y's are in L2. I don't care what color it uses. So I'm just going to leave it exactly like that. So there's no change you have to make there. But we do have to look at our window. What's the highest x value?
A.
And the lowest? I would go 0 to 10 on the x's. What would be good for the y's? Yeah, I'd say 0 to 170. That'd be pretty good. 0 to 170. And now if you hit graph, you should see the points you plugged in. There are the points, the little squares. Now, let's type in the equation that we found. What was the equation?
Y equals 5.
It's 5.
5x.
Yep.
So 5 is.
The 5/3. Now those points look pretty good to me. They almost look like they're on a perfect curve. So this line, this curve is probably going to be really a good fit.
Because I gave him the 5/3 Riley. That's still high quality.
Yep, so that's almost perfect. So we just found a curve that goes through all the points. And because the calculator did it, that is the best possible curve you could ever find. So what you could do now, if you were doing an experiment where maybe this was the number of bacteria, you could say, well, I know at 1 hour I had this many, at 3 hours I had this many. I could use my formula now to figure out at 2 hours how much bacteria I'd have. I could interpolate, or I could extrapolate and say, how about after 12 hours? What's going to happen? Assuming the pattern continues.
I went down the stat plot and it says that mine are off for all except for 5. How do I turn them on?
So turn one of the stat plots on, you go to y equals, and you just make sure that it's highlighted at the top. So you just have to press up, and now I just turned mine off. And then if I hit enter, it's back on. And if you turn it off and on, it has to redraw everything again. So that's what it's doing right now. Okay. Any question on that? So the way you'd see this on a test, I'd give you a table of data. I would ask you, is a power model the right thing to use to represent it? You'd check like this. You'd show me. You'd say, okay, looks like they're in a pretty straight line. And then you'd go ahead and find the power model. Now, if you check it and the points are not in a straight line, then that means when you find a power model, it wouldn't be good. It would be a curve, but it might not be a good fit for the data. There's probably something better. Okay. And again, what else is there? There's all kinds of fits you can do. Okay, all kinds of stuff. Power models is one of dozens of things. Yeah.
So we would just say that it's not a good fit, and that would be our answer?
Yeah, if it wasn't a good fit, you would just pretty much stop there.
Okay.
Now, if the directions say to you, find a power model, then I don't care if it's a good fit or not. I'm asking you to find the power model. Just do it, okay? So this question didn't say find the power model. It said find it if it's appropriate. And it was appropriate here. So, any question on that? Okay, so that's a calculator thing you have to know for tomorrow. If you say, oh, I can't remember where calculate is, I'm not going to tell you tomorrow that you press stat and then you hit the right arrow to get to calculate. Okay, you have to know that. All right, so two things. You go to edit to type the data in, calculate to calculate a power model, and mine is option A, a power regression. All right, so we're going to take a look at the first part of 5.5, whether or not you even differentiate it as a new section, it's up to you. It's really still logs. And we already looked at the change of base formula. Technically, not a formula that you need. If you don't know it, you can get around using it. I showed you guys how to do that. So, if somebody gave me a problem like this, like log base 3 of 2. And I said, you know what, I don't know how to figure that out. I don't remember the change of base formula. I could change it back to an exponential. And then say, well, the only thing I don't like about that is the variable and the exponent. But there's a rule, I can move it in front as long as I take the log of both sides. Now I could take the x and put it in front. And now I have a very easy problem to solve. Divide each side by the log of 3. Log 2 divided by log 3. That's exactly what the change of base formula is. Log of the argument divided by log of the base. Okay. I think the change of base formula is much faster. Okay. But you can get around it if you forget it. So let's graph that and find domain and range. Now, we have to use the change of base formula just to type that in, because we don't have a base 3. So I'm going to go up to my plot. I'm going to shut that off, because I don't want to keep seeing that. Okay, go down to y1. And how would I type in y equals log base 3 of x?
Would it be ln of 3 over x, or is it x over 3?
X over 3.
X is higher than the 3.
So it's argument over base.
So the thing that's higher always goes on top. ln x over ln 3. You could have done log x over log 3, same thing. Okay, let's do zoom 6. So what is my domain there?
0 to infinity.
Including 0?
No.
No, cannot take the log of 0. Now the range, you can't quite trust what you're seeing. What is the range?
Negative 2 to infinity.
All right, let me zoom in right there. Just go down a little bit. So you said it looked like it stopped at -2. Now what does it look like it stops at?
-3.
Okay, I could keep zooming in and doing this all day.
Oh, it's infinite?
It's infinite, right? The range, that's a vertical asymptote. When it gets steep, the calculator can't draw it. Remember, logs always look like this. They go down forever. So it kind of looks like a square root function or something, the way the calculator draws it. But square root functions actually do start at a point and go in one direction. Logs don't. Logs go forever up and down. Yep.
How did you just zoom in? Just by putting the cursor over it?
I did zoom 2. Yep.
Oh,
And then I hit enter near where I wanted to zoom in.
So why is it 0 to infinity?
For the domain?
Yeah.
Because if we look at it, it goes to the right forever, so
Yeah.
that's infinity. But it doesn't go to the left forever.
Oh, okay.
Remember, you
That's
cannot
a
take the log of a negative. If you try to take the log of a negative, it's imaginary. If you try to take the log of 0, it's a domain error. You can't take the log of 0. And, I mean, that would be a good question, like to ask, like, why can't you take the log of 0? With any base you want? What would the answer be? Well, think about writing this in exponential form. What's your base? A. What's your exponent? X. What goes on the other side? 0. So, let's say that, I'll make up a number just to make it simple. Let's say your base was 3.
Oh, so it's not possible.
3 to what power gives you 0? Nothing. It's impossible. You can't raise 3 to a power and ever get 0. That's why you can't take the log of 0. Okay. So, we got the domain, we got the range. We're good. Okay, so all the standard transformations, we keep saying the same thing. They apply to logs. What does the A do?
shift horizontally.
Horizontal shift. What's the B? Horizontal stretch. Could be a horizontal reflection if the B was negative. What's C? Stretch. And D? Vertical shift. Remember, horizontal stuff is always the opposite of what you would think. If you do a +2, that's going to move it left. +2 for horizontal would move it left. If you put a big number in for B, like 20, a big number actually compresses. Okay? Big numbers compress it. Vertical, it's not like that. Vertical is exactly what you would expect. Okay? And we've done this many, many times. Yep.
So when C is negative, it does it go over the x-axis or y-axis?
A vertical reflection is over the x. Yep. So, let's take a look at how you could graph this function starting with this function. Not a lot of transformations happening. Just one thing.
Reflective over the y.
That's inside is, let me think, inside is horizontal.
Reflect over the y.
So that's a reflection over the y-axis. So let's write that down. So, to graph y equals log base 3 of negative x, do one thing. Reflect the original log base 3 of x over y-axis. Now, when you're graphing, you would never compare something with like a base 3 to a base 5. If I have you graph and say, how would you do it? You'll be comparing a base 3 to a base 3, or a base 2 to a base 2. Right? The bases wouldn't change. Okay? Now let's just think about it a little bit. It's a reflection over the y, right? So which way is it going to curve? It's going to curve to the left. So if you know the domain and range of the original, we should be able to figure out the domain and range here. What's the domain now? Not including 0. And the range? Yeah, no matter how you reflect this, it's always negative infinity to infinity. If something goes negative infinity to infinity, you can't change that. No matter how you shift or stretch or flip it. Can't. Okay, so find the domain, find the range. Oh, and the vertical asymptotes. Vertical asymptote starts out with what letter? X. A lot of people on the test, when I asked for a vertical asymptote, they picked the option that said y equals. That's horizontal. So x equals is vertical. And where is the vertical asymptote? 0. It's at 0. Okay. If you shifted it left or right a little bit, that would change. But we didn't. We did a mirror image. So it stayed right there. Okay, let's list the transformations here. Log 3 minus x. What's a little weird about writing it that way? It's backwards, right? We usually put the x first and then the a. So let's write it like this. How many transformations are happening? 2. What's the first one? So shift left 3. And then what? Yeah, you could say reflect over the y. You could also say horizontal reflection. Same thing. Reflect over y-axis. So remember, if you were to graph this, it might actually look like it moved right 3 because you're going to move everything left 3 and then flip it. So that is correct though. It's going to go left 3 and then mirror image itself. Yep. Okay, so when we graph log functions, a couple things we like to find to help us. Vertical asymptote is probably the most important because that tells you what your graph is going to curve up against as it goes down. And then intercepts, you'll always have a y-intercept because logs go up and down forever. So you're going to cross the y-axis somewhere. But you're always going to have an x-intercept. Sorry. You might not have a y-intercept. Imagine you had a log like this. It's never going to cross the y-axis. Okay, but it will always cross the x. So, to find the vertical asymptote, set the argument. That's that part. Argument is what's inside. Set that equal to 0 and solve. Okay, remember x-intercept, y-intercept. X-intercept, plug in 0 for y. Y-intercept, plug in 0 for x. If you need more points, you can pick more. Just make sure that when you pick a point, it actually works. Right? If you plug in a value for x and it causes you to take the log of a negative number, that's no good. So logs only curve in one direction. Kind of like square roots. They only go one way. Okay, I usually need more points. I like to have about 5. That's pretty good. Okay. So let's sketch a graph of that. Let's start with the vertical asymptote. That's the easiest. How do I find the vertical asymptote? Set the argument equal to 0. It's the value of x that would cause you to take the log of 0. So x equals negative 5/3. Okay, or what is that? Negative 1 2/3. So negative 1.7 when we graph it. Wait, let's do that right now. Okay, I'm just going to kind of sketch by hand. It's not perfect, but it's about negative 1.7. Okay, we've got that. Let's try to find x. That's probably going to be annoying. Let's try to find the y-intercept. Didn't ask for it, but that's a point that's going to help me. So where it crosses the y-axis. What do I plug in? 0 for x. So I'm going to get 3 times 0 plus 5 is how much? 5. So the y-intercept is log base 2 of 5. So we just learned how to do that. Log 5 divided by log 2. The y-intercept is about 2.3. Okay, range. Range we shouldn't even have to think about. What's the range of every log function? Yeah, always. Now the domain you should be able to figure out once you get your vertical asymptote and know which way it curves. Right? It can only curve in one direction. So I know that this function is going to the right. So my domain is everything from what number? Negative, yeah, 5/3 to infinity.
So how do you know which way it goes again? This one or nine?
Well, I know it's going to curve to the right because I just found my y-intercept.
Oh.
If I didn't have a y-intercept and it came out as an error, then I know it would be going this way.
Oh, okay.
Then it would never cross.
Okay.
Right? And what I can do now is I'm going to get maybe two or three more points. I could do it by hand, plug in 1, plug in 2, or just type it into my calculator. Log 3x plus 5 divided by log 2. Okay, we already got the y-intercept, 2.3. We got 2, 3.4. 2, 1, 2, 3.4. And because I know logs are basically pretty flat, I mean, they're not really flat, but they go up real slow, we can go right to 10, and it's not going to go up that much. 5.1. Okay, so draw your graph. Remember, it's going to drop down like that. Okay, let's do zoom 6, see how we did. Yeah, it's basically it. Remember, that's not accurate. So if you copy something like that on the test, I know you don't really know what logs look like because logs go down forever, right? They always have vertical asymptote, so that means it drops down forever. Okay. Any question on that?
I mean, guaranteed I forgot.
Okay, I think, yeah, last thing. So, last thing we're going to look at is a specific equation that uses logarithms. And this is an equation for calculating the intensity of an earthquake. Okay, so if you've seen on TV or read in a book like the Richter scale, like a magnitude 5 earthquake or something, that's what this is. So there are 4 variables. R is the magnitude. That's the number that you usually hear like on the news that people know how powerful it was. A is a factor that they give you in the word problem that measures the ground motion in micrometers. The amplitude of the ground motion in micrometers.
So that's the equation that will give us?
Yeah, they'd give you that equation and they'll basically give you the A, the T, and the B. T is a period of the wave in seconds. Now if you're like, well, what wave? Well, imagine like you drop a rock in water, right? You see a wave coming out, like a ripple on the surface of the water. Well, the ground does the same thing in an earthquake. It's just you can't really see it if you're on the ground. But if you were like up above the ground and you saw like an earthquake happening, you'd see a wave of movement coming out from the center of the earthquake. But you'd have to be above it to really see it. And B is a factor that accounts for the weakening of the wave. Because there's going to be a big difference between the wave being like in like a desert. I would think in a desert, the wave energy would be absorbed by the sand. Versus if it's in like a really compact, hard rock, I would think that energy is going to transfer. Right? Like if you were standing on the other side of this table and I push it, this table's hard. So the energy is going to go right from one side to the other. But if we were in sand, like a wall of like, sand between us, and I push on the sand, you're probably not even going to feel it because it's going to get absorbed. Right? But so B accounts for like the kind of material that the Earth is made of. All right. So what they're going to tell us in this problem is that at the early stage of an earthquake, the amplitude of the vertical ground motion is A. That's all we know. Okay? It was A. At a later point, it was 10 times as much. Bless you. My question is, how much did the intensity change if the ground motion basically increased by a factor of 10, the vertical ground motion? Assuming all else equal. Okay, the consistency of the ground would stay the same, the period of the wave would stay the same. This is the only thing that changed. So when the earthquake started, it was 10A. It was 10? No. A. Later, it was 10A. So, any questions on what it's asking first? So, if you want to figure out a change between two things, what operation do you usually use? Use what? Subtraction. Okay, some kind of subtraction. So we're looking at how the intensity changed. So we're going to have, how do we want to write this? I'm going to have two intensities. Okay, what variable did I use for intensity? R. This equation is the intensity, and the equation is R equals. So R is intensity. So, let's see. So if you want to figure out the change, we just have to figure out what order we subtract in. Do we do like what it's at the beginning minus later, or later minus the beginning? Well, did the earthquake become more or less intense here? Became more intense. So I think we should start with the later and subtract what it was. No, not that. That. Start with what it was later and subtract what it was earlier so we get a positive change. If you do it the other way, it's fine. You're just going to get a negative change, which is the same number, but you're kind of looking at it the wrong way. All right. So we're going to do, this was later in the earthquake, minus earlier. Right. So let's figure out what the intensity of the earthquake was later, when it was more powerful. So it's the log. What was the vertical ground motion later when the earthquake was more powerful? 10A over T plus B. That's all going to stay the same. Minus, now let's do what the intensity was earlier. Log, what was the vertical ground motion early on? A divided by T plus B. Okay, now let's start to simplify that. Lots going to cancel. What do you have to do with this minus? Distribute it. So what's going to happen?
B is going to
b's are going to disappear. You're going to have log 10a over t minus log a over t. All right, now let's look at each one of these. Let's start with this one. That's a quotient. If you were going to split that apart, how does a quotient split? Subtraction. Log of 10a minus log t minus, how would this other one split?
Log of A and then
Log of a
minus log of B.
minus log of t. Now, that same question I just asked before. What do you have to do with that negative? Distribute it. What's going to happen when you do that? You're going to have negative log t minus minus. It's become a plus. So minus minus log t becomes plus. So you're left with this minus what? Log a. And that variable should cancel out because it stayed the same. I said that everything is staying the same. Now, let's combine those back together. That's subtraction. How does subtraction recombine? Division. Log of what? 10a over a. What happens there? Cancels out. So all you're left with is the log of 10. That's how much more powerful the earthquake got. So let's see what that is.
Can you just look at the factor that it moved up by?
1. So what that means, because we got a 1, it means that if your earthquake is 10 times more powerful, that's a difference of 1 on the Richter scale. So it doesn't seem like much, but if you compare a magnitude 2 earthquake to a magnitude 3 earthquake, that's 10 times as powerful. How about if you compared a magnitude 2 to a magnitude 4? 100. Every number on the Richter scale is a factor of 10 times as much. That's how it works.
No one has to take
That means that there's technically no
Okay, so homework for tonight. Page 293 is the first part we did. You're going to have to find a power model for some data. And page 301 is what we did with the graph. Okay, reminder, I will be after school today for extra help. So if you need to come, I'll be here. Otherwise, anything you need to finish, it's got to be done by tomorrow, or it's a 0 for your term 1 grade. This test is going to go on term 1.